this is an Archer 2 training course, and I'm just going to give a very quick overview of what that means, how this course comes about, and a bit of the background to the service. So Archer 2 is going to be the next UK supercomputer service. There's been a slight delay on the hardware. It's been exacerbated by COVID-19. And we won't be using Archer 2 for this course for various reasons, but it will be housed, operated and supported by us, by EPCC, and the hardware will be a Cray machine. But as part of that service, the Archer 2 service, we provide 60 days training per year, meant to be at various locations around the UK, but of course, with the current situation, we're doing these courses online. This is a picture of what Archer 2 will look like. It'll be located at the EPCC Advanced Computing Facility, which is a facility maybe 10 kilometers south of Edinburgh, where we're based. This is Archer, which was one of the potential. This is the current UK national supercomputer, also a Cray machine, a very large machine about that. Archer 2 will have about 750,000 CPU cores, closer to 1 million. Archer has about 100,000 CPU cores. It's getting quite old now. The machine we plan to use for this course is this machine, Cirrus, which has about 10,000 CPU cores. But you may have been seen in the media, there's been quite a few security incidents around the world, and quite a few machines, including our Archer and Cirrus, have been taken offline temporarily while the system is checked out. Luckily, we were able to find a backup system for this course. Apologies if that causes any issues, but we've had to arrange it at rather short notice, and I'll talk about that later. What is EPCC? We're the closest thing that the UK has to a national supercomputer centre. We've been around since 1990. We originally called the Edinburgh Parallel Computing Centre. That's where the acronym EPCC comes from, but technically we're EPCC. We're part of the University of Edinburgh, and we've been running national parallel systems since, coincidentally, a Cray machine, a Cray T3D, in 1994. We have over 100 full-time staff doing academic and commercial projects. And as part of that, we do postgraduate teaching and we do HPC training courses. And this is obviously one of those training courses. If you want to get in touch with us, please do at the end. If you're based in the UK, then if you're a researcher, then EPCC staff work just like standard research associates, postdocs. So a lot of our staff work half-time on something and a half-time perhaps collaborating with the UK research group on a research project. We also do a lot of European projects as well. These are the Archer 2 resources. You won't need them for this course for two reasons. We're not using Archer 2, but also the exercise, this is not a course about Archer 2, it's a course about message passing, programming, and MPI, and things would just be shrink wrapped to work out the box. But the main thing there is to note that material from all our past training courses is archived on the Archer 2 website. Who am I? Well, my name's David Henty. I'm in charge of education and training at EPCC. That involves our MSc, our Appraised Training Centre, I'll mention later, and the courses on the Archer 2 training programs, commercial training. My research interests are really around parallel programming models, accelerators, and performance, just general, getting the best out of parallel computers. Other resources, please fill in the feedback form at the end of the course. We've seen in the past that we get much lower feedback returns of feedback from online courses than from face-to-face courses, but we really would appreciate feedback about anything about the course, because we have taught online courses before quite a few times, but we're moving to teaching them all online, and so we are exploring various different methods, and we'd like feedback on what works. We also run a one-year postgraduate master's course, the MSc in HPC, MSc in HPC with data science, awarded by the University of Edinburgh. We've run that for almost 20 years. This is a picture of a recent, a few years ago, graduates. We run two versions. One is a standard on-campus residential version, but also we're just about to launch, I mean, it's quite timely with COVID-19, but we were always planning launching a fully online version, online part-time intermittent studies starting September this year. That's a standard UK MSc, which the UK being the UK, I mean, it attracts quite large study fees, but it's a standard MSc. We also run a supercomputing MOOC. This was developed under the PRACE project. It typically runs for 5 weeks. It's very conceptual. There's no computer programming required. It might not be appropriate for this audience, but it might be appropriate for your colleagues or people who want to learn about supercomputing. It's run 5 times with support from EPCC answering questions and stuff. That's no longer sustainable, but it should be available soon in the self-study mode. So, futurelearn.com courses supercomputing. Hopefully very soon there will be a run advertised, which will be, the whole course will be there, but you will follow it at your own pace, and we won't be able to provide detailed hand-holding support, but the FutureLearn platform builds up a very community spirit, so hopefully you'll interact with other learners there. During the course, we've given you personal accounts for the duration of the course. Normally, if it was Cirrus, you'd get machine access for up to a month afterwards, and then you'd have a couple of weeks to take off your work. Hopefully next week, we will be running on Cirrus and we'll transition to Cirrus. So we've given you personal accounts to allow you to do practical exercises in between the lectures and afterwards as well. We haven't used temporary accounts at the moment, so how that will work with these temporary accounts, I can't guarantee. But these accounts will be open to you outside of the course, and hopefully you'll get a Cirrus account. Well, you will have able to get a Cirrus account. You will be able to run on that afterwards. Again, you can do all these exercises on your own laptop. There were some instructions circulated about that as well. So you need to make sure if you're working on one of our systems, you take your work away at the end. You will have some time to do that. But the main thing is the course materials will be available forever on the Archer 2 website, so don't worry about having to copy materials. Longer term, you can get access to the UK supercomputing resources Archer and Archer 2 via standard methods. Most of these require a lot of justification, but we do run something called the driving test, which is supposed to break this vicious circle that you're not allowed onto a supercomputer until you know how to use it, obviously because it's quite an expensive resource, but how can you prove you can use it if you can't get on? So we have a small driving test and you get an account for 12 months with an allocation of quite a lot of CPU core hours. We will have a driving test for Archer 2 when Archer 2 comes around. I believe the Archer driving test is currently still running. If you're interested, maybe if you're in the UK, if you're interested in learning about what's happening on Archer, well, you might want to know about our training program, because a lot of the training is quite generic, but you might not want to have an Archer account. You can actually sign up to our training email. So there's a link there. You can sign up and you will get all the Archer 2 emails which are relevant to training. And as I said, much of the Archer 2 training, obviously in the initial period when the hardware isn't up and running yet, will be quite generic and applicable to a range of platforms. This is an email statement about the security of the room. This doesn't apply. You're all sitting in your own houses, I guess. So we have a code of conduct we expect everyone to adhere to. This may look like motherhood and apple pie, but it is very important. We're all coming from different backgrounds. We all have different experiences. And so please, show courtesy and respect towards other community members, be constructive. And this applies to the trainers and also obviously to attendees. And there's on our webpage, there's full details and a way of, if you're concerned about anything, you can report things which you might be worried about. If you're a UK researcher, you will be able to apply to funding to help you develop, or your group develop software for Archer 2. That will open very soon, and there's a link there. It's called the ECSE program. If you're in the UK, it's just a continuation of what we ran on Archer. So I do hope you enjoy the course. Please ask questions. How questions work in the online courses, it's probably best if you use the chat. I mean, we can use audio, but definitely initially it's maybe best if you use the chat. I will try and monitor the chat windows. I can't guarantee I'll see everything immediately, but please ask questions during the lectures. Ask a question when you want to. I'd rather discuss things that you're interested in, you need to know about, than just carry on through the slides. But I mean, I have a colleague, Queven, and who will be hopefully monitoring the chat as well, so hopefully we'll pick things up. So this course is also part of our PRACE program. PRACE is the Partnership for Advanced Computing in Europe, has 25 members, and the UK is a partner in PRACE, and UK is represented by EPCC on behalf of the UK research councils. As part of the PRACE project, there are 10 PRACE training centres, PTCs, around Europe. We are one of them. There are 10 of them, all of whom run a program of courses, and you can see the URL there. they're all trying to move to online training at the moment, but that's, you know, that's all up in the air at the moment. But there's a centralized website, training.prace.ri.eu, where you can see all these courses. Prace supports us. It funds travel, catering. You're not getting catering on this course, I'm afraid. But again, you can see upcoming courses at EPCC or throughout Europe at those URLs. So that's just a very quick sort of word from our sponsors, as it were. We seem to have quite a good attendance. What I wanted to do, because it's an online course and I can't see people, was basically to maybe do a small quiz. So if you just give me a few seconds while I set up. So if you could go to so I'm getting stymied by Microsoft's insistence that so I've just got a little quiz here to basically, you know, I'll be doing a couple of quizzes during the course, but this one is just really a getting to know you quiz. So if you could point your browser at www.socrative.com, do a student login, and I'll ask you for a room and do HPC quiz. So I see a few people already coming in, which is good. And I'm just asking a few questions just to get to know you. This will only take 5 minutes, but I thought it'd be useful to get some idea of what's of your background and where people are from. So what will happen is we'll ask a question, and later in the course I'll use a quiz to actually try and test people's knowledge or hopefully back things up. But at the moment I'm just using it as a way of getting to know you all. So that does seem to be working pretty well. So I'll just wait a few minutes and then see how people are getting on. That is one of the disadvantages of giving an online course. You don't get that instant feedback from people. So we've got about 25 people. That's good. Let's just see what happened. Okay, so there's about, hopefully you should be able to see that. Okay, no, I've done the wrong thing. I need to, what I need to do is to share the correct screen. So give me 1 second. I will do that. Excuse me, I've just slightly less organized than I normally would be. Apologies for this. Okay, so you can now see the answer. So see, basically we've got 10% Scotland, half people from the UK. Actually, there's people from so actually most, there's actually more than half of you from, I guess people are from Northern Ireland, and then people from Wales. That's very interesting. Okay, so let's do the next question. I just wanted to understand what people's position is: undergraduate, postgraduate, research assistant, lecturer, working for a company or other. It's just interesting to these are the kind of questions I normally ask people as they come in and have a coffee before the course starts, but I couldn't invite you for a coffee for a whole number of reasons. these quizzes are all anonymous as well. So that's not relevant here, but when we come around to do the where we're actually asking technical questions, you know, if you don't know, just guess, because this is all completely anonymous. I don't know who people are, and that's really just to try and promote. So okay, so most people, we have a couple of people in the company, MSc, mostly postgraduate, PhD, and research assistants. That's typically the and we have other people. Okay, that's interesting. So we were learning MPI. MPI requires you to do C or Fortran or C++. There are ways of doing MPI from Python. I mean, I've thought about transitioning the course, but it's not totally standard. So, you know, I want to know if you're going to use C, C++, or Fortran, but of course, Fortran comes with a multitude of sins. So this is my my definition of so the course is effectively language neutral between C and Fortran. But it is useful to know if people are Fortran programmers, what they're where they're really old school kind of. I fit into the category. I'm not really a C++ programmer. I'm a C and Fortran programmer, and I would class myself as Fortran programmer of class D. You know, bit of array syntax, allocates, and a few modules, nothing too fancy. I would class myself in that. Okay, now that's very interesting. Okay, so I mean, I've given this course before. Most recently gave it to our MSc students, and there it was almost entirely C or C++, and we have a large. Okay, that's very useful to know. Very useful to know. So we have, you know, quite a large community of Fortran programs. I guess that reflects the fact that people are doing research in HPC and or doing scientific research, and Fortran is still a very popular and language in that community. That's very. I'm glad I asked that question. That was very, very useful. So okay, there's something called OpenMP, which directs us for shared memory threads programming. I'd just be interested to know, you know, what your experience of it. You know, I may sometimes say MPI is different from OpenMP in this way. I'll try and avoid it's. If you haven't done OpenMP, it's absolutely fine. There's no issue there. It does not require this, but it's often a useful counterpoint to illustrate how the two are different. So it's just useful to know if people have. Okay, so 2/3 of the class have used it. So I will try and. Apologies to those who've not used it. I will very minimally use it as an example. Don't worry, it's just because most of you have used it. I may use it occasionally as just a counterpoint example, but you know, it does not really doesn't matter if you don't pick up on it. To be honest, actually, if you've done OpenMP, people often get more confused. If they've done OpenMP programming, they can get confused because MPI is surprisingly different from it. So actually, that can actually be a hindrance if you've done it, but it's useful to know as a counterpoint. Just interesting what systems you use. I mean, Archer and Dirac are UK systems. The first three are UK systems. I just want to know if people are users of these systems. They're actually, the list C is incomplete because there have been a more Tier 2 system funded in the UK. But of course, you know, this course is open to anyone. So I'm interested if you maybe a European praise system or another supercomputer, perhaps not maybe one of your local systems, or you might, again, there's no need to be a supercomputer user to use MPI. You can run on your laptop if you want. I'm just interested in people's background. Okay, so we have quite a few Archer users. Archer, so about 45% of people are, almost half are kind of users of UK systems. A small fraction using European systems, and not. Okay, that's again interesting. That's interesting. More users of supercomputers than I'd expected, but that's very useful to know. And just your current coding work. You know, maybe you're actively developing your own MPI code, but you you're self-taught and you want to learn. You know, you may be working with an existing MPI code. This is the classic. I'm a PhD student and my supervisor has given me an MPI code. You're planning to develop one, or maybe you're just here out of interest. Okay, that's very interesting. Okay, so that's a nice, if that was a marking spreadsheet, that was a nice Gaussian with most people working, and that's fine. That's great. Okay, that's very interesting to know. Okay, that was useful. So I think that is the end of the quiz. Okay, that was useful. So that worked. Because it's set as a quiz, I have to set right answers for everything. I think, which of course is not relevant when you're using it as a survey, but I will. Okay, just give me half a second because while I check my machine is. Okay, fine. I was worried my machine was overheating, but it's not too bad. So what I will do now is I will do the first talk. Well, actually, and I'll walk you through what we're going to do. So. I'll just show you what the overview of the quiz is. Sorry. So this MPI course has a long history. We've been teaching it since the mid-90s. An MPI course, not this one. I inherited it maybe 15 years, 20 years ago from people, and other people have worked on it. What we're going to do is the first day we will, this is the syllabus, okay? So we're taught message passing concepts and basic MPI programs, point-to-point communications, mode tags, and communicators. We'll do that today. Then we'll do non-blocking communications, collectors, virtual topologies, and derived data types tomorrow. And then the way I've set it up is we have a gap, and then we have a case study on image processing and a couple of extra talks, hopefully once you've had time to assimilate the material on general MPI design issues and performance measurement and scalability. The syllabus, the aims are, it's a practical course to teach you to understand the message model for parallel programming and to write parallel programs in C or C++ or Fortran using the MPI library. So you'll learn this through lectures and notes, but I said most importantly by writing and executing example MPI programs. Every lecture has an associated practical example. I do distribute simple solutions. I'll show you where they are. But, I think that, attempting the practicals is really the most important thing in this course. What's the motivation? Well, the motivation is the MPI library is the most important piece of software in parallel programming. You might say, well, I would say that because I'm teaching the course, but really, 99 point, I don't know how many 9% of cycles on the world's largest supercomputers are used by programs using MPI. It is completely universal. It's actually quite an unusual situation, but it is. All the world's largest supercomputers are programmed using MPI. And I think writing parallel programs using MPI is fun. It's an interesting, some people find it very simple to assimilate conceptually, some people find it a bit more difficult, but I think it is fun. So I'll just take you through what I will do is it'll be easier if I use a browser here. So if we go to everything you'll get from the Archer website. So you'll seen this page already. We're on the MPI course. And you'll see the timetable. Now it's split Thursday, Friday this week, and then Friday next week to try and give you a chance to do the exercises. I have stuck with the normal timetable I use for a face-to-face course, where other than maybe the first session, this one, which is slightly lecture heavy, we will do maybe in an hour and a half. So we have 9:30 till 11 and a half-hour break, 12 till half 11, sorry, half 9, then half 11 till lunch at 1. Apologies for those of you maybe in mainland Europe, that's going to be a bit later for you. Then 2 till half 3, another break, 4 till half 5. And typically those sessions will be 3/4 of an hour lecture, maybe a bit less, and 3/4 of an hour practical. Now, we debated how to do this. I think we'll see how this model works. Hopefully you'll try the practicals, and we can try and give you support through chat. There are breakout rooms. We'll see what we can do, or you can go and do something else. It's really up to you. But hoping that people will attempt the practicals in that session. Then we have a week's break, and to give you, and then we'll finish up next Friday. I'll give you this case study, which is more of a real example. Now, there are two useful things here. The course chat is a useful page where we can hopefully collaboratively just type in stuff. So if I have ad hoc so I wonder if it might be useful if somebody could go on and check that they can access that. Fine. So that's good. That's good. So this is just, this will be a useful place for posting ad hoc pieces of information, which may come around with us using a different system this time. So that's very useful to have working. I will try. Okay, so I'll now go back. But the main page is the course materials page. Now, under Archer, we stored all of the Archer 2 service only recently started. This is one of the first courses. My colleague Julian did the first course under Archer 2. This is probably only the second training course under Archer 2. We've moved to storing stuff on GitHub. Now, so you should be able to see that I am not a particularly sophisticated user, but the main point is that all the material should be available from GitHub. So we have all the lecture slides, and then lower down the exercise material. So I'll point you to that later, but one thing which might be useful is I've put up this is the machine we're going to be using, guest accounts in the next gen IO system. What I will do now, we will spend the practical session. So we're not going to do any programming practicals in this first session. We won't actually be using the machine until about maybe midday, in the midday till one session, and that's where we'll get everyone logged on or help you use your laptop. Actually, what I should have asked is on the quiz is who is using their laptop and who is using their our machines. So actually, that would have been a very useful thing to ask. But I will maybe do that as a quiz later on. But if you want to try, you're welcome to try log. It doesn't work, just wait and but those are the instructions for logging on. And I've given you all assignments of account names to users. So now I've tried to maintain some anonymity here because I didn't want to give away everyone's identity. So I've just given you people's initials and place where they're from, but the guest accounts are ngguest10 up to ngguest43. So that page there, you should be able to get what your guest account is. You don't know what the password is yet, but I will stick that up in the chat session just so you have a copy of it. So the password is the same for all the accounts, and that's what it is. So you're welcome to try and log on to the machine now. If it doesn't work, please bear with us and we can give you support later on. But I've put the password in there, so it might be worth taking it, and that should be the same for all the accounts. So hopefully I've navigated all the materials. That looks different links for the sessions, the course chat. I think that's everything there. But I mean, this is the main course page. As I said, I think really the place which is your home page for this course is the course materials page there, which I will. I hope there's no mistakes there. I've had to change it a bit because of our use of the new machine. So I will tell you needs to be updated. So I will now, if there are no questions, I will now give the first actual lecture. So I'm having a few problems here. So apologies, I seem to have a slight. No. So hopefully, yeah. So okay, fine. So I'm now going to talk about message passing concepts. Now this is quite important. I know some of you want to get onto programming and such like, but it is very important to get the concept straight in your head. So I will go through. So hopefully this lecture will be about half an hour. Then I'll do a 10-minute lecture on a maybe this might be more like 35, 40 minutes. Then I have the thought experiment. So what I'm going to do in this first session is purely conceptual. I'll tell you about the concepts behind message passing programming and MPI. Then we'll have a little, I'll give you a little problem, which I'll actually return to on traffic modeling. It's a simple cellular automaton model to do traffic modeling. We'll return to that. I'll use it as a reference quite a lot in the course. So even if you have some knowledge and some experience, it's worth paying attention here, because definitely the traffic modeling example, I think, is a key example which I will use. So I'll cover the message passing model. I'll cover SPMD, a single program, multiple data. I'll talk a bit about communication modes and a bit about collective communications, all hopefully at a conceptual level. So what I'm talking about here is, imagine that this was a course on serial programming. Now, it's not a course on serial programming. Imagine it was. There will be 3 levels I'll be talking about. The first, and imagine you'd never programmed before. I would tell you about concept independent of any programming language. They're just things that when you write programs, you have arrays, subroutines, variables. It's a human readable piece of text. You have object orientation, okay? And those will be, I would talk about them first. Then I would say, okay, you've learned about the general concepts. We're now then going to illustrate that using a particular language. We could use Python, Java, C or C++, Fortran. You might have things like structures and if then else for control flow, okay? That would be the second level. Then I would have to say, okay, I've told you that we're going to use C, but on this particular machine, this particular target platform, we're going to use the Cray C compiler, or the Intel C compiler, or the GNU compiler. So there are 3 levels here. The conceptual levels, which are language independent. There's the actual programming languages themselves, which are a standard. And there's the implementations, which are particular compilers, like the GNU compilers, the Portland compilers, the Intel compilers, the Cray compilers, which implement that. And the same thing is true for message passing parallel programming, okay? First of all, we have concept, and that's what I'm going to talk about in this lecture. We have things like processes, send, receive, SPMD, groups, and collectives, okay? Then, the interesting thing about message passing is there's only one library here. So, you know, it's not, I'm not going to talk, if I'd given this lecture 20 years ago, there'd have been lots of libraries here, things called like PVM, parallel virtual machine, and lots of things in here. So there is only one real library that people do parallel programming in, MPI, and it has various function calls. MPI init is one of them we'll come across. That has both good and bad points. The good point is, if you want to do message passing parallel programming, you learn MPI. But if you want to do programming, you have to say, should I learn Python, Fortran, C, C++, Java? What should I learn? But the bad point is that you should still think at this conceptual level. A lot of people want to dive in and learn about MPI. You should be thinking at this level. You should be saying, look, I want to implement sends and receives. I want to have multiple processes. How do I implement that in MPI? Okay, so I'll try in this first talk to be conceptual. Having said that, though, the MPI library is just a standard, just like the C programming language, the Fortran programming is the standard, and there are multiple implementations, okay? Intel have an MPI library, there's an Open MPI library, there's a Cray MPI library, we'll probably be using Open MPI. It doesn't matter, okay? At this level, we don't really care as long as it works. One quick point here, though, the standard MPI library, which people download from the web, from the internet, is called Open MPI. That was a really, really, really stupid naming convention, because there is this programming model called OpenMP, which allows you to write parallel programs using threads, okay, for shared memory computers. It has nothing whatsoever to do with OpenMPI. OpenMPI is a library which implements the message passing interface standard which we use for message passing parallel programming. It has nothing whatsoever to do with OpenMP, and that causes a huge amount of confusion. OpenMP came first. When they wrote OpenMPI, they shouldn't have used that terminology. I'll come back to that. So what is the message passing model? Well, the message passing model is based on the notion of processes. Okay, so when you launch a program, when you run a program on any computer, you get a process. A process is an instance of a running program together with the program's data. Now, interestingly, a modern computer can run lots and lots of processes. If I just quit this and have if I look at this, it's actually a virtual machine, but what am I running on my virtual machine at the moment? Task manager. You can see that I am running ludicrous numbers of processes on this machine, dozens and dozens and dozens of stuff, none of which I know what it does. You can see my Firefox there, and I'm running, yeah, I mean, I'm really interested in it, but this computer is running dozens and dozens of processes. All modern computers do, okay? So running multiple processes, running processes is nothing new, okay? However, all those processes in the normal situation are separate programs which are just sharing this computer. In the message passing model, what we want to do is we want to do a parallel program. We want to use multiple processes, physical processes at the same time. We do that by running multiple processes, and we achieve parallelism by having many processes cooperate on the same task. So that's the big difference. We're not going to use a computer to run lots of separate processes, my web browser, my editor, my Microsoft Teams application. We're going to run lots of processes, but they're going to work together on the same task. Each process only has its own access to its own data. If you're an OpenMP program, that means that all variables are private. So the way that modern operating systems work is separate processes are very ring-fenced from each other. Okay, that's deliberate. It's to make sure that if you write if your internet browser crashes, it can't trash your Microsoft Word document. Okay, processes are incredibly shrink-wrapped from each other. What we want to do is want them to work together, but each process has its own data. They can only communicate with each other by sending and receiving messages. And so that's what the message passing model is about. You have lots of programs running, which are separate operating system processes. And when they want to talk to each other, they send messages. And that is a bit like making a phone call or sending an email. We'll use various analogies throughout the course. These are implemented as library calls from a conventional sequential language. There's no reason why you shouldn't have a parallel programming language, a new one, to do message passing programming. People have invented hundreds of them. People hate new programming languages, okay? It takes decades for new programming languages to come around. In the past 3 or 4 decades, we've had C++, Java, then Python taking off in the scientific community. People hate learning new programming languages, so the successful approach has been to do parallel programming, particularly with MPI. You don't learn a new programming language, use your own favorite programming language, and you have access to special function calls which do the magic of communicating, and their library calls. So the sequential paradigm when you run a normal programming model is that you run a program, you think of your program becomes an operating system process, it has memory, and you think of it as running on a processor, and you think of it as being when you write a program, you think of it as being the only program in the world. When you run it, you don't worry that it might be running on a computer with lots of other programs. This is your model, okay? This is how you think of when you write a sequential program. This is your programming, this is your mental model of what is going on. And if you do that, if you believe that, you will write a correct program. The equivalent message passing is we run multiple processes. We run a program multiple, so we run maybe 4 processes. I've numbered them 0, 1, 2, 3, and it turns out that that's what MPI does. When you run a process, it numbers them sequentially, 0, 1, 2, 3. But we want them to work together, okay? You can run multiple processes on any computer. You just launch lots of programs, but we want to work them together cooperatively on the same task. They need to talk to each other, and they do that using MPI, the message passing interface. It gives us library calls, which allows them to talk to each other. Now, in reality, for processes to talk to each other, they might be on different computers in different parts of the world even. there will be some physical communications network which links them. And so that might be on an Ethernet network, on an InfiniBand network, or on a very high performance supercomputer. It might be a much more dedicated have the Cray Aries or the new Slingshot network. The important point about MPI is it insulates you from the communications network. MPI guarantees that messages will be delivered between parallel processes, and you don't care about the communications network. That gives you portability. A correctly written MPI program can run on your laptop, on a departmental machine, on the world's largest supercomputer. You just recompile, you run, it will work. It will use whatever network is there. It's just like when you send an email. You don't care how the email is delivered. Is it email delivered over 4G, over Wi-Fi? You just send an email, it gets there. It's the same with MPI. And the reason MPI has been so successful is that model maps very closely onto what real parallel computers are like. Now, this is not a hardware course. I'm not going to talk about how parallel computers are built, but it's useful to have this mental model that a modern distributed memory parallel computer is a picture of the previous national supercomputer in the UK, Hector. I use it because it's quite a nice picture. But the way a modern parallel computer works is you just have lots of separate computers with their own processor and their own memory. Think of these as lots of laptops, okay? 1, 2, 3, 4, 5, 6, 7, 8 laptops connected through some interconnect, some physical network, okay? So we have here 8 individual computers, each running their own operating system, completely separate computers, just like 8 computers in a lab, 8 laptops, but they can talk to each other through some network, and on a modern parallel computer, that will be a very high performance network. But this mental model of separate processes communicating through MPI maps very neatly to the reality where we would run, we would run separate programs on distinct nodes of this parallel supercomputer, and for them to talk to each other, the message would have to go over a physical network. So the mental model that MPI uses maps very well onto the physical architecture of modern supercomputers, and that's why, remarkably, MPI has been successful for over 25 years. So this is a very important slide. The way it works in MPI is, imagine we have 2 processes. I call them process 1 and process 2, and I want them to communicate with each other. So in program 1, process 1, it has a variable a, and it says a equals 23. Think of process 1 as running on your laptop, okay? So this is running on your laptop. So on your laptop, a variable a is set to 23. Think of process 2 as being your collaborator's laptop, and they could be on the other side of the world, or they could be in the next office, but they're on a separate laptop. I want to get this value a equals 23 from my laptop, which has its data, its physical memory, to your laptop. Your laptop cannot read the memory on my laptop. If you were allowed to do that, all hell would break loose, okay? So laptops are very distinct from each other. How do I get data from one laptop to another? Well, I could just email you if it was a document. In MPI with a program, what happens is I get access to some magic routine called send. I say, I would like to send this data A to process 2, okay? And we'll see the exact syntax later on in MPI, but that's the model. You call a function or a subroutine send. And what MPI does is it then takes that data and sends it. And you can think of this as like sending an email, okay? So I'm going to ask a question here if people want to answer in the chat. If I want to communicate between me and my collaborator, okay, I want to take data in my brain, a equals 23, to send it to my collaborator's brain. If I send them an email, does that transfer the data from my brain to their brain? Write the email, dear Jane, the value of a is 23, send. Has that transferred the data from me to them, from my brain to their brain? Yes or no? And if no, why not? Yeah, absolutely. So it might seem quite a trivial comment, but that's really, really important, Laura and Dale. They have to read it. And so MPI is a 2-sided process. Messages are sent, actively sent, but they have to be actively received. So for this, and that's why I've actually shown this this data going into, not into process 2's memory, but into what you can think of as an inbox. The email analogy, it sort of goes into an inbox. We'll discuss what actually happens later on. So because process 1, I'm not allowed to scribble in process 2's memory. Okay, process 2 has to, and in MPI that's called a receive, or in message passing. So process 2 has to actively say, okay, I want to receive a message from process 1, and I'm going to put that data into my variable B. And this means process 2 has total control over its memory. It decides when to receive the message, who to receive it from, and where to put it. And so this has transferred data because I have a send and a receive. The data A equals 23 on process 1 has gone into B, the variable B on process 2. Okay. Now you might ask, what happens if there's a send and no receive? What happens if there's a receive and no send? But we'll cover all that later on. Now process 2 can say A equals B plus 1. So process 2 has a variable A and its value is 24. This is actually another important thing, because these are separate programs running in separate processes and on separate computers potentially. Just because I have process 1 as a variable A does not mean that the process 2's variable A has the same value. And so simple questions you like to ask in normal programming, like what line is my program on, are meaningless in message passing parallel programming, because process 1 could be on line 53, process 2 could be on line 97. They're running their own independent programs. Secondly, the question is, what is the value of A is meaningless. You have to say, what is the value of A on process 2, on process 1? And we'll come back to that. But this is actually quite, so just to say that, go through that again. Process 1 is running a program. It says A equals 23. It decides to send the data to process 2. Process 2 is running a different program potentially, or a different point in the same program. It issues a receive, and only at that point is the data transferred. And it can set a variable A. Its own variable A can be different from process 1's variable. So you could imagine a message passing system where if you're running on 10 processes, 10 computers, you have to write 10 programs. That turns not to be scalable. And remember, I said Archer has 100,000 CPU cores. Archer will have 750,000. You're not going to write 100,000, 750,000 separate executables. So the way that most message passing systems have worked, and MPI in particular, is they use single program multiple data. Every process runs their own copy of the same program. You write one program, you compile it, but at runtime you run multiple copies. But because you're running multiple copies potentially on different computers, each process has a separate copy of the data. So it's a single program, but they all have their own data. SPMD, single program multiple data. You might say, if every process is running the same program, why don't they all do the same thing? Well, each process has its own unique identifier. We saw we can label them 0, 1, 2, 3. That's what MPI does. MPI calls it the rank. And processes can follow different control paths through the program depending on their process ID. So, you can say, if I am process 2, do this, else I do that. So although they're running the same program, they can do different things, okay? We also usually run one process per processor core. So if you had said, I've got a parallel computer with 20 CPU cores, I would run 20. Now, there's no reason to do that. On your laptop, you might have 2 or 4 CPU cores. You could run 100 MPI processes, okay? Why not, okay? You can run as many processes as you like on a computer. Modern computers are running hundreds of processes all the time. But in MPI, where we're doing scientific and technical programming, if we have 4 CPU cores, we would typically run 4 MPI processes, okay? Why do you think that is? We could run 8, 16, 32, 100 if we wanted. But if we have 4 physical CPUs, we're only going to run 4 MPI processes, okay? Why do you think that's the typical thing to do in scientific and technical programming? When we could run as many as we like, and that's useful for debugging. But for production, if I've got 4 CPU cores, I'll run 4 MPI processes. Anyone think why that is? It's to do with how fast the program is going to run. Yeah, so Lawrence is asking a question to do 1,000 things to do. Yes, so I think that's the memory limited. That's a very good comment. And communications takes time. Yes, they're all, but the reason is that we're doing in scientific and technical programming, we're interested in performance. If we have 4 CPU cores, we want our program to go 4 times faster, okay? If we run 8 processes, all that happens is that they'll have to share the CPU cores. We just have to time slice. If a physical processor runs more than one process, it just has to swap them in and out. So if we write a parallel program and we run 4 copies of it on 4 CPU cores, it might go 4 times faster. If we run 8 copies, it'll continue to run, but it won't go any faster. If you have 4 CPU cores, I can only run a program 4 times faster. If I run on 8, it will run, but it might slow down, even exactly as Laurent says, asking someone to do 1,000 things, they're flat thrashing. And as Kazuki says, the communications takes time. So, you know, for debugging, it's really important to realize you can run as many MPI processes as you want on your laptop, which is very useful for debugging purposes. But if you're interested in performance, you need to know how many CPU cores you have when you run the same number of processes. You might say, wait a second, I want to do something where I have a controller worker model. I have one process which gives out the tasks, and the other processes do the work. So let's think of me being the controller and you guys being the workers. I give you all tasks, you give them back to me when you're finished. That clearly has 2 programs. We have a controller program, me, whose job it is to give out the tasks, and a worker program, you, who processes the tasks. That sounds like you need, well, in MPI, you just stick them into a single program. You have a single message passing program where you say, you start up, you say, look up, if I'm the controller process, I run the controller function. If I'm the worker process, I run the worker function. So if I ran that task farm model, controller worker model, then one process, me, will be in the controller function, and all the other guys will be running this function. So if you want your process to do distinct things, you just stick them in the same program and have an if statement. And in Fortran, it's just the same thing, okay? So SPMD is not a restriction on the general message passing model, but it makes things simpler in practice. So I've talked a lot about messages, but I haven't really said what they were. A message transfers the number of data items for a certain type from the memory of one process to the memory of another process. The important point in the MPI is that messages are, to a modern programmer, would seem quite low level. A typical MPI message is 4 integers, 10 floating point numbers, 6 double precision numbers, okay? It is not a method or some fancy thing, it's just data, because that's what most scientific and technical programs do. They transfer data, okay? They're doing technical computation. So that, now it can be a bit more general than that, but if I say MPI message to you, you should think of something which contains 4 integers or 1,000 double precision numbers. There is extra information, who sent the message, where it's going, what the type is. We see there's a message type identifier, but fundamentally an MPI message is a bunch of data. So when you send messages in MPI, there will be some header information, which is like the ID and such like, some metadata, but fundamentally an MPI message is a very low level thing. It's a bunch of data, typically of the same type. Now, in everyday communications, there are multiple ways of sending messages. If I want to communicate with you, I could send you an email or I could phone you up, okay? And they're actually fundamentally different models of communication. And so I'm going to talk a bit now here, and we'll come back to this in MPI, but it's very important to realize, even conceptually, that when you send a message, there's multiple ways of doing it. In MPI, we call them synchronous or asynchronous. Synchronous is like making a phone call, okay? Synchronous send is not completed until the message has started to be received. If I could communicate with you synchronously, I make a phone call, I wait on the phone until you pick up the receiver, then we talk. So there's a synchronization in time. An asynchronous send completes as soon as the message is gone. It's like sending an email or writing a letter. It's a fire and forget model. So in MPI, you have the choice. There are at least 2 ways of sending messages: synchronous, which is like making a phone call, or asynchronous, which is like sending an email or writing a letter. Received are usually synchronous. The receiving process must wait till the message arrives. That may surprise you, but that's the way. If you issue a receive, then you wait until the message comes in. But at the sending side, it can be sent synchronously or asynchronously. So synchronous send is actually making a phone call is actually maybe a better model. I have this animation. In the old days, I know this isn't true anymore because faxes scan, but in the old days when you sent a fax, you went to the fax machine, you put the fax in the machine and you waited, and a few minutes later you get a beep. And that beep was very important. You got confirmation that the message had been received. It was synchronous. You waited until the message had been received and then you took your document away. Possibly for synchronous send, making a phone call is more of a useful modern analogy. Asynchronous send is very like posting a letter. You only know when the letter has been posted and not when it has been received. Okay, so when it's like sending an email, you send it, and unless the person actually explicitly sends it back, you just don't. Off it goes, and you hope it's delivered. Okay. So we'll come back to how those are implemented in MPI, but immediately you can see there's an issue. If you make synchronous send in MPI, like making a phone call, and nobody issues a receive, you wait. And it may surprise you, in MPI there are no timeouts. So if you issue synchronous send and there's no receive, you wait forever, and your program deadlocks. It just stops. Okay. Similarly, if you receive, and receive is by default synchronous, it's like standing by the phone and waiting for a phone call. It's a bit you wait forever. And so the problem in MPI is it's up to the user to match the sends and the receives. If they don't match up, your program will typically not work and typically deadlock. It will just stop working because you're waiting for a message to be received and there's no receive. You're waiting for a message to come in and there's no incoming message. Okay. And we'll look at that in practice in specific examples. Now here we've considered point-to-point communications, one sender, one receiver. It's the simplest form of message passing. It relies on matching send and receive, and there's analogies sending personal emails. However, there's often cases where you want to do something more general. And so, for example, there's a lot of instances, particularly in scientific and technical programming, when you want to do a global communication. And this can be built from simple messages, but MPI was written to facilitate scientific and technical programming. So in message pass, we have the concept of collective communications, and they're given their own status. So a barrier may not think of communication, but a barrier means everyone stop, and until everyone gets here, we'll all move forward. So we all collectively issued a barrier at the start of the lecture. I waited for everyone to come in, and then I started lecturing. Okay. We'll come back to barriers. There are barriers in MPI. There are some issues with them, which I'll come back to, but there is a barrier. The most useful, possibly the most useful, one of the most useful lectures is broadcast. That's what I'm doing at the moment, okay? I am broadcasting. I could deliver this lecture by every time I had a line to send, to say, I could individually message you with the next line in the lecture. I could go through all the attendees and send you a personal chat message. This is the next line in the lecture. That would work, but it would be very, very inefficient. So the way we do lecturing is we do a broadcast. It's a one-to-all communication. There's one sender and multiple receivers all operating at the same time. But the most important point about this slide is, in message passing speak, we are all currently participating in a broadcast. It's a collective operation. We're all participating in a broadcast. Within the broadcast, we have separate roles. I'm talking and you're hopefully listening, but within that, we're all collectively participating in a broadcast. You often do this at the start of a program. If you might nominate one process to read in the data, and it broadcasts, said, look, alpha is 93.5 and n is 100, and you all broadcast it. So broadcast takes data on one process, the 8, and copies it everywhere. You may not want to broadcast, you may want to distribute data. So I might have an array 0, 1, 2, 3, 4, 5, and I don't want to copy that. If I broadcast that data, you would all get a copy of 0, 1, 2, 3, 4, 5. I might want to send the first element to the first process, the second element to the second process. That in message passing is called a scatter. So in a scatter, you scatter the data. So if I did a scatter on that data, different processes would get, here I'm process 2, the one we get different data on different processes. You often do that at the start of a calculation. You read in some data and you say, look, I want to distribute the data to different processes. And we'll see that in one of the examples later on. Similar at the end of the program, You might want to gather, we've all finished, you say, look, I want to gather all the data back so I can write it out to file. Let's nominate one guy here, process 2, as the person that can't apologies, I'm just having an incoming chat message where I have to so apologies for that. So at the end of a calculation, you might want to gather all the data back. So if you issue a gather, it's the inverse of a scatter, the data gathered back to together on a single process, who can then do what they like with it, like write the data out. Okay. However, possibly the most important operation which you do in scientific and technical programming is a reduction operation. Everyone has their own data. Remember, in a parallel program, you have multiple processes all with their own data, but often you want to combine it together. Okay, so for example, I might want to know what the average age of everybody in this course is. To do that, I need to take you all have your own age, but there's only one average age. So that's important. In a reduction operation, you all have your own data, but there's one answer. It's like a vote. Okay, we all have a vote. Should the UK continue to be a part of the European Union, and we all have our own vote, and there's only one outcome. But maybe a more useful example is average age, and so we all have our own age. If I add those together, okay, if I add those together and divide by the number of people, I get the average age of people. And you do that all the time in scientific and technical programs. And you might be simulating the weather. Each process is simulating a different part of the country. Each process has its own rainfall, but you want to know what's the average rainfall across the whole country. You need to accumulate the data together and reduce it, for example, add it. I could do a max. That would be. I might want to know what's the age of the oldest person in this course, probably me. We'd get them together. You all have your own ages, but there's only one maximum. So a reduction operation takes distributed data, combines it, and produces a unique output. And we do that all the time, and we'll do that in one of the exercises. So we could form a global sum, product, max, min, etc. Here we do a global sum. The average sum of 0, 1, 2, 3, 4, 5 becomes 15. Oops, sorry, 15. So just to reiterate the process we're going to go through, to launch a message passing program, in most message passing systems, and in MPI in particular, you write a single piece of source code with calls to some message passing functions such as send and receive. Okay. You then compile with a standard compiler, because it's just a C or Fortran program, or C++ program, but you have these magic functions which are provided in a library. Message passing is typically, an MPI in particular, is implemented through a library. You link to a message passing library provided for you. There's lots of libraries. Open source and vendor supplied libraries exist. For this course, we don't care. Okay. If we have an MPI library that works, we're happy. Okay. Just if I was doing a C course, I wouldn't care if you're using the Intel compiler, the GNU compiler, or the Microsoft C compiler. Why would I care? We then, having compiled one executable, just compile it, link it. We then run multiple copies of the same executable on a parallel machine, or you can actually run it on your laptop. Each copy becomes a separate process. There's multiple copies of the same executable. Each copy has its own, is a separate process. Each has its own private data, completely distinct from the others. So each copy can be a completely different line in the program, and they can take different paths. If I'm process 1, do X. If I'm process 2, do Y. Okay, they all go off and do their own thing. Now, you don't have to. If I'm on 1,000 CPU parallel computer, I don't have to log into program 1 and run it there. Sorry, log into computer 1 and run program there, computer 2 and run the program there. MPI provides a launcher program. So what we say is we have a launcher program, and we'll see it's called something called MPI run probably, which says, look, could you please run n copies of this executable called myprogram.exe, and it will distribute them and launch them, and it will work for you. But the model is n independent copies of the same executable. Issues: send and receive must match. If you don't match your send and receive, the program may deadlock, it may just stop. It will store forever because MPI has no timeouts. It's possible to write very complicated programs, but most scientific and technical programs or data processing programs have a simple structure, which results in simple communications patterns, which are supported often in collective routines. So you can write most scientific and technical programs using quite simple use of send and receive plus collectives. Okay, if you start writing a very, very complicated program and lots of it's spaghetti communications, you probably need to rethink what you're doing. You should use collectives where possible. They're elegant and they're implemented efficiently. We'll come back to that. Summary: messages are the only form of communication. If you're not calling a send or a receive, you're just running a program, doing your own thing. You're sitting in your office, working away. When you want to do communications, you actively pick up the phone or send an email. Okay, so MPI has two distinct modes: calculation, where you're just running normal code on your own data, quite happy. Communication, you issue sends, receives, or collectives. Most systems MPI use the SPMD model, single program, multiple data. All processes run exactly the same code, but they don't do the same thing because you have a unique ID. MPI calls it the rank. I'm process 1, you're process 7. You can take this different branches in the same code. The basic communication form is point-to-point. Collective communications implement complicated patterns that often occur in many, many codes. So the summary is, message passing is a programming model implemented by MPI, which is a library. It's essential to understand the basic concepts, which are private variables, explicit communication, SPMD. And actually, most people's major difficulty is understanding the message passing model. It's a very different model to sequential programming. So this is in some pseudo language. This is a perfectly reasonable piece of sequential code. If x is less than 0, print error and exit. Stop running. That's a very dangerous thing to do in a message passing program, where we're running this multiple times. Why do you think that is? Okay. Why is this a dangerous thing to do in a message passing program? What could go wrong? Yes. So Dale says it could end some process and not absolutely. Why could it do that? So that's exactly correct. But why? What? There's no yes, but still, Dale's comment still stands. If x is less, Dale, absolutely, each process has its own value. Absolutely. So x is a local variable. You might have arranged for x to have the same value everywhere, in which case this is a safe thing to do. But in general, x. So half the processes quit, half the processes don't. The processes that haven't quit have no idea that other processes have quit. So the next thing I might do is I might issue a receive from a message from a process which has quit, and then we get deadlock. So some things in MPI and message passing are simple, some things are surprisingly complicated, and clean termination of programs is surprisingly complicated because, exactly as Leonardo said and Dale, each process has its own X value. Some of them might be negative, some might be positive, and so it's actually quite complicated. So there's a question here, can I use MPI on a shared memory? Yes, you can, absolutely. So what will happen is, say you have 8 CPU cores, you'll run 8 processes, and hopefully your operating system will run, if all things go well, will run a different program on each CPU core. Actually, MPI works fantastically well on shared memory computers, because when you want to send the issue someone mentioned before is when you send a message, there's a delay. If you phone somebody, there's a delay. On the shared memory computer, there is still a delay, but it's very small, because MPI can just communicate between the processes through shared memory. So you write exactly the same MPI program. You could run it on 8 separate computers connected by a network, or one computer which has one shared memory computer with 8 CPU cores. All that will happen is it will run faster on the shared memory machine because the communication is faster. Now, and so we maybe discuss this towards the end of the course, but MPI programs run fantastically well on shared memory computers. Of course, you're limited. The reason that we use distributed memory is if you want to run on 1,000 processes, you can't get it's hard to get a shared memory computer with 1,000 processes. Modern, typical shared memory nodes go up to a few hundred now. So that's why MPI, our model is this network. but yes, exactly. And in fact, I develop all my programs on my laptop, and only when I want to worry about performance will I go onto a more onto a genuine supercomputer. Does that answer your question, Lee? So no. So on a shared memory, we'll use no. So MPI is very clever. You know what MPI will do is, you know, so actually, you know, as a modern supercomputer is actually a distribution of computers across a network, but each computer will have multiple CPU cores. So for example, Archer 2 is going to have I'm going to get this wrong, either 64 or 128, I should know, many tens of CPU cores per node. So when you send a message, MPI will look and say 128. Fine, yeah, I always get these factors wrong of CPUs per socket, sockets per node, and hyperthreads. So yes, it's 128. I didn't want to miss. Yeah, 64 core. It's 264 core AMD processors per node. MPI will a modern MPI implementation will say, okay, that process is on the same node as me, so I will just, who knows, do a copy in and out of shared memory or something like that, and it'll be much quicker. It won't use the network. It won't use the network. So you know, you can run on a completely but that's the magic about MPI. If the process is on a different computer, it will use the network, and it will, you won't see any difference other than one will be faster than the other. So that's an excellent question, Tom. I want to start the new lecture, but the important point is that writing OpenMP is easier than MPI. It's an incremental model. We'll see that if I gave you a serial program and said parallelize using OpenMP, I would go in and stick OpenMP directives in, and gradually the program would get faster and faster. The disadvantage is you can't run on more than one computer, so you're limited to how many CPU cores you have in your shared memory node, which is going up, but it's, you know, maximum about 100. So if you knew you never wanted to run on more than 100 CPU cores, you probably wouldn't do MPI. But if you take the hit of do MPI, it's much more work. You have to break your program apart, possibly redesign the algorithms, bring it all back together again. Once you've done that, though, it runs fantastically well on a shared memory machine. So OpenMP is much easier to write, but limits you to a single node. People say 10 times. I mean, you know, but that's why OpenMP is a really simple way. Plus, there are things you can do in OpenMP you can't do in MPI. You can have shared variables in OpenMP. Two CPUs can actually physically share the same data, which can make things a lot simpler. So OpenMP is simpler and easier to write, but doesn't let you run on more than one node. So Lee's I'm going to come back to this. How to make sure the MPIs run in different cores. So people always ask this, but I always say, well, my laptop is running Internet Explorer, Shell, a web client, 100 programs. How do I make sure they run on different cores? It's up to the operating system. A good operating system will schedule them to different CPU cores. A good operating system. Introduce this example, then I'll take you through the exercise sheet. That will take us up to 11, and then you can do it. We'll revisit it after the coffee break. So traffic flow. We actually I don't know if that is the sound coming through. I forgot there was sound on this video. Predicting traffic flow is very useful for a whole bunch of reasons. On a short term, if you can predict traffic flow, you might be able to optimize traffic sequences to get better throughput. That's a bit like weather forecasting. At a longer level, you might want to do something like climate prediction. You're saying, if I build a new road, how is the traffic going to change? So traffic modeling is a very important topic. And you want to look for effects like congestion. This is actually a video from Bangkok, I think, where you want to avoid you know, congestion. So what we do is we build a computer model. Okay, so we build a computer model which simulates the traffic and allows us to make decisions about what we want to do, how things are going to work. Okay. Now, what we're going to do is we're going to consider a very, very simple traffic model. Now, a disclaimer, this talk was originally written for a public engagement and outreach lecture. So there are some very, very poor attempts at humor in this lecture. So apologies for but I like the animation, so I kept them. We're going to it's a very, very simple cellular automaton model. It's the simplest one you can imagine. We're going to divide the road into a series of cells, and they're either occupied or unoccupied, okay? And we have one rule. We do a number of steps, which you can think of as being time. At each step, car moves forward if the space ahead is empty, and not if it can't. So the important thing is an instantaneous update. We don't say that car can move. Then we look at the car, say that car can move, that one can't, and that one can, and then we move them. And now we say that car can't move, that car can, and we move them. And now, of course, you can see they can all move. Off they go. Okay. And we could do this by moving pawns on a chessboard. In fact, yeah. So you may be aware of the game of life, which is designed by John Horton Conway, who unfortunately died a few weeks ago. But that's quite a sophisticated cellular automaton in 2 dimensions. This is a very, very simple model. So that is it, basically. We'd hit that, and then off they go. Okay. Now, this traffic model predicts a number of interesting features, surprisingly. So at traffic lights, you get the right behavior. The lights go green, and although all the cars are lined up at once, they move away in a line. So that's relatively realistic, actually, surprisingly realistic for such a simple model. But also it predicts congestion. So what we're interested in is congestion. So what we're looking at is, this is the density of cars, okay? 0% is no cars, 100% is every cell is full. So the density of cars is the number of cars divided by the number of cells. So the density here is 0.5. We have 4 cars on a road of length 8. Okay. If the density is less than 50%, eventually the cars arrange. So this is like an asymptotic graph. Eventually the cars arrange themselves car gap, car gap, car gap. Okay. So they can move at speed 1. So the speed is the number of cars that move divided by the number of cars. So if all the cars move at speed 1, if half of them move at speed 0.5, if none of them move at speed 0. So you could have guessed immediately that 100% filling, none of the cars can move, and up to 50% density, you could have guessed that the speed would have been 1. What is not obvious is actually congestion sets on very rapidly. So above 50% for even this incredibly simple model, congestion sets on very rapidly. So it's surprisingly sophisticated. In reality, you do much more complicated models. But okay. So we can actually classify, if you want to think of it as being a cellular automaton, you can classify it as saying, well, we're going to represent this as a bunch of cells, whether they're occupied or not. And the way a cellular automaton works is it tells you what the new state of this cell n is depending on its neighbors. Okay, but actually I'll not go through this because this analogy isn't particularly useful at the moment. It's maybe a bit too much for this course. Okay, so I'll skip over this and I'll skip over the state table. This is 2 different ways of thinking about the model. But what we're interested here is, I'm going to give you some pseudocode at the end, which is probably for this course the most important way to think about how fast can we run the model. And when we talk about computer speeds in flops, floating point operations per second, thankfully we're going to measure the speed of this model in car operations per second. How many cops can we operate this model at? So what I'm going to imagine is I'm going to got a chess player here. And this is Bobby Fischer, who was a very eccentric, very successful chess player in the 70s. He is going to do the traffic model by using pawns on a chessboard. He's got a chessboard, and for each car, he has a pawn and move them. Okay, so in that model, he moves that one and that one. Then he moves that one and that one. Then he moves that one and that one. And off they go. How fast can he do it? Well, I reckon that one Bobby Fischer could do 2 car operations per second, 1,001, 1,000, something like that. Okay. That's not what we're interested in. If we had 3 Bobby Fischers, could they run the model at 3 times faster? Could they do 6 car operations per second? And the way to think about it is, here's the parallel traffic model. So what I want to do is I want to simulate a, sorry, I have a slight issue with my cursor. I want to simulate a road with 15 cells, okay? But I'm doing parallel programming in the message passing model. I actually have 3 people, A, B, and C, who only have, each of them have a road of length 5. So I've just said that I've got 3, I'm going to write a parallel program. There's 3 of you. Each of you has a little chessboard, and you only have a road of length 5, okay? You should think of these people as being in different offices, potentially in different parts of the world. Person A is in the UK, person B is in France, person C is in Seattle, okay? They can't see each other's roads. How are they going to do this traffic? Well, immediately you see there's a problem. Person A doesn't know if they can move this car because they don't know what's happening here. Person B doesn't know if they can move this car. And person C doesn't know if they should put a car in here. So immediately you have a problem. The only way you can simulate this traffic model is to communicate. So they have to communicate. Person A and person B have to talk to each other. Person B and person C have to talk to each other. And then they can, so the way that parallel programs typically work is you have this communication phase where you exchange your data, in this case, data about your extreme, and then you have a calculation. And we are able to get the same answer, oops, I've done that very well, as I'm showing what happens in the global model at the top, but by doing this communication calculation, we get the same answer. So I'm going to leave you before the break with a piece of pseudocode. So the only difference here is I'm going to do traffic on a roundabout. That turns out to be relevant. On a roundabout, cars go around in a circle. So to do traffic on a roundabout, all you're saying is you have periodic boundary conditions. When a car disappears off here, it reappears here. Okay. So we're going to do traffic on a roundabout with periodic boundary conditions. And what I'm also going to do, my machine's got something weird here. I'm going to have 2 arrays, old and new. So old is the state of the model at current time step, and new is the state of the model at the new time step. And what I'm going to do is that although I only have n cells, I'm going to declare arrays, apologies, of size n plus 2. So I want to simulate n cells, say n is 15, but my arrays are bigger than they need to be. They have a fake 0th cell and a fake n plus 1th cell. Those are typically called halos or ghost cells. And in this model, it would be like having an extra cell here and an extra cell here. The reason is we have to have special conditions at the edges, because we have to say, look, if when I look at this cell, its neighbor isn't that cell, it's this cell here. And when I'm looking down from here, I get that cell there. I could do that by having different code at the boundaries. But what I do is I actually have extra cells at the end, ghost cells, and so I have a little ghost cell, an extra cell 0 here, and a cell n plus 1 here, and I fill in the back. So I copy the data from cell n into cell 0, and the data from cell 1 into cell n plus 1. That means I can run the same code everywhere. I can just say, what's the status of cell n plus 1? And I've made sure it's the correct data because I've done an explicit copy. Now, in the serial code, it's a matter of judgment. Do I have separate, different code at the boundaries, or I have these extra boundary cells which I copy in and copy out? In the parallel code, it turns out to be a much greater, a better simplification to have these explicit ghost cells. So what I do is I loop over iterations. At each iteration, apologies, I have to set the boundary. I set old of 0 is old of n, and old of n plus 1 is old of 1. That's setting periodic boundary conditions. Then I loop over the cells, and I can just do the Celler automaton update. And this says, this rule here says, if the current cell is free, okay, if the upward cell is, sorry, the current cell is occupied. If the upward cell is occupied, then I stay occupied, so the new one is full, else it's empty because the car has moved. Or alternatively, if the current cell is empty, sorry, my Windows machine is playing up. My current cell is empty. If the previous cell is full, then it moves, else it stays empty. You might think that's a bit strange because if you think about it, the Celler automaton should have 8 rules, and there's only 4 rules there. Well, actually, this is a particularly simple cell because if the current cell is full, I only care about the state of the cell up. the current cell is empty, only care about the state of the cell down. So though in a general 1D cell or automaton there will be 8 rules, here there are only 2. So then we end. So that's the pseudocode I want you to look at. I've given you that. I'll leave. You should look at that. But the exercise sheet is on the website. I'll very briefly show you that, and then we can take the break. Apologies, I'm a few minutes late. But if I find the website, I don't have it open. Yeah, there's the GitHub website. We have the at the bottom we have the exercise, the traffic modeling exercise sheet. And what I want you to look at is it basically reiterates what we've just talked about. But you should, I wouldn't bother about the rules for cellular automaton. That's something for another day. But really, I think you should think about section 2 and 3. Okay. Look at that. In a longer course, I'd ask you to write the pseudocode. I've given you the pseudocode. What parts of the calculation can be done independently? What parts require some form of cooperation? What's the best way to handle communications? Well, I've actually hinted that I think you should have the explicit ghost cells. Is it possible to? So also, and then think about the message passing implementation. How would you divide the data amongst processes? I've already hinted at that with my diagram. When is communication required? I also want to compute the average velocity, the total number of cars that move divided by the total number of cars. How would I do that? But also think about how you would, do you think about how you're going to communicate between processes, what communication is needed, but also how would it work if you sent data asynchronously or synchronously? Because there's a subtlety here. The fact we're on a roundabout is actually, it plays a role here. So, you know, you can take a break now. We'll come and discuss this after the break at 11:30. What I expect you to do is to look at that pseudocode and then think about the diagram I showed you where I had multiple people, these 3 people each with rows of length 5, and think about parts 2 and 3. What implications does that have for parallelization? How would you send and receive the messages in MPI? Are there problems, potential problems with deadlock? And we're going to come back at 11:30 and we will talk about those points.